Yeah. So welcome everybody. My name is Mike, and to start things off, I want to give you a quick background of my research. Germany is currently facing one of the largest infrastructure programs in recent decades. A large number of new transmission corridors are being planned as part of the energy transition. Many of these transmission lines, and that's important for my research, are built as underground cables and stretch over hundreds of kilometers. What you can see here is the planned grid expansion in Germany. The main idea is simple. A lot of electricity is produced in the north, especially from wind power, but it is needed in the south where the demand is higher than in the north. So the electricity has to be transported over long distances along the whole country, across the whole country. And in the next step, I would like to show you why these conditions make planning for us as engineers so complex. First of all, these corridors they're passing through very different types of areas, from rivers to cities to protected areas. And at the same time, the second point, there's a lot of time pressure. So the grid needs to be built quickly, but planning and approvals, as we already heard in presentations today, often take years. So the third point is there are also technical challenges. Ground conditions change, there are many crossings, and there is no one solution that fits it all. The fourth point, finally, the choice of the construction method along the corridor is a key issue. It directly affects cost, time, and environmental impact. And this is exactly where one of the main challenges in this corridor planning lies. We will see that later when it comes to my research, why the link to the construction method is, for me and my research, significant key. So to give you a better idea of how these corridors are built and what I mean by construction methods, here you can see two typical examples. On the left side, open cut constructions, where a trench is excavated and, let's say, make it simple, and the pipes are put in. And on the right side, a trenchless method like horizontal directional drilling, short HDD, which is used for crossings, for example, under rivers or under roads. So depending on the conditions, different construction methods are used. But the question is, how do we actually decide this along the corridor? And this is where we run into a little problem. Because in this context, we are not talking about where the corridor is located. The corridor is already defined following years of planning. The key question is how we do actually build it. After the corridor is fixed, the planning phase focuses on the execution, based on things like geodata, environmental rules, and geotechnical reports. But these information are quite general and abstract. In the actual executing phase, so on the construction side, we need very concrete values. We need to know the exact method, we need the effort, the time, and the cost. And this is where the problem starts. There's no clear link between these two levels. As a result, planners, consultants, and especially construction companies, they have to go back and forth again and again during the execution. And this is exactly the gap my research addresses, the bridge between these two levels. The goal is to turn planning data into clear and measurable decisions by linking data, construction methods, cost, and time in a structured way. To understand what already exists in this area, let's take a look at the literature. If we look at the literature, we can see three main types of approaches. First, there are methods that compare different construction options and rank them. Second, there are rule-based approaches that check what is possible under given conditions. And third, there are more advanced methods that use optimization and sometimes look at individual segments. But one thing is common to them all. Most decisions are still made for the whole project. They do not decide step by step along a long corridor, as we earlier see a corridor with 100 kilometers. They don't do it step by step. They make decisions for the whole project. To make this more concrete, here are a few examples. Approaches such as Alinici and Linner focus on comparing and ranking alternatives. Mathias already goes one step further and assigns method along different corridor segments. This is already quite close to my idea. However, none of these approaches provides a complete solution for corridor scale decision making. So the question is, what is still missing? When we summarize the gaps, most approaches still treat construction method selection as a project-level decision rather than a segment-level decision. In addition, there is usually no consistent logic that links planning data directly to construction methods. And finally, cost, time, resources, and digital planning. These tools are rarely integrated in these approaches. So as a result, they are difficult to apply in real projects. These findings clearly show what is needed: a corridor-based approach, a transparent decision logic, and a direct link to cost and time, and maybe a time schedule. And this is exactly where my research starts. So based on these gaps, for me, the next step was clear. We now move from analysis to a possible solution. In the following, I will show you the main idea of my research and how it addresses the problems we have just seen. The main idea, I think, is quite simple. We break down the corridor. We break it down into smaller sections in modules. Each section has clear conditions like soil, crossings, and surroundings. Based on this, we assign a suitable construction method. Then we add simple values like cost, time, and resources. In the end, we get a clear and comparable unit along the whole corridor. So the key question, what exactly is a module? A module is basically one piece of the corridor where the conditions stay the same. This includes things like the ground, the geometry, and the construction method. For each module, we can then define things like cost and time. And the key point is that each module can be evaluated independently. This makes it possible to move from general ideas to clear and measurable decisions along the corridor. So how do we get to these modules? Just in a visualization, we start with simple map data from GIS or OpenStreetMap. From this data, we can identify crossings along the corridor, like rivers, roads, or railroads. Then we group nearby crossings together based on technical limits, for example, the maximum drilling length. And this gives us the sections along a corridor. Based on these sections, we decide how the corridor is built. In simple terms, the key question is, can we use open cut, as we already saw, or do we need to drill? And this is how the models are defined along the corridor. To add, all of this happens automatically in just a few seconds, based only on the route in a map. So we only got a line, and all these decisions or all these modules are produced automatically within seconds. This slide illustrates the whole picture of this concept. What we do next is to treat each of these modules as a separate decision unit. Each module combines the local conditions like ground and geometry with a clear way of building it, either open cut or drilling. This means we no longer look at the project as one big problem, but as many small and consistent decisions along the whole corridor. And because of each module is clearly defined, we can link it directly to values like cost and time. This makes the whole process more structured, easier to compare, and scalable. To wrap it up, what I presented today is a proof of concept for energy corridors. The bigger research question is whether this modular planning framework can be generalized to other infrastructure projects. I believe that modularization is a fundamental way to reduce complexity in big infrastructure projects. And my goal is to develop a generic framework that can be adapted in different domains. So for the last slide, what does this research bring in the end? It helps to turn planning data into clear and measurable decisions. It creates a structured way to link data with how we actually build and with things like cost and time. This makes planning more transparent, more consistent, and easier to compare. In short, it helps to make better and more informed decisions along an infrastructure project. So in the end, thanks for your attention, and I'm happy to get some questions from you.